Hello, chemistry gang. In this lecture, we are going to look at an example of titration curves. And this example is a strong example, meaning that we have a strong acid and we have a strong base. Remember that in a titration, one of the starting materials or reagents needs to be strong in order to ensure a complete or quantitative neutralization reaction, so we can relate moles of one thing to moles of another. So here we have strong, but we could also titrate something weak. So we really have two examples that we need to get through. In this lecture, we're doing the strong example, and in a subsequent lecture, we will do a weak, strong example. Of the two versions, the weak, strong example is definitely the much more difficult process. So the example here is to sketch the titration curve for the titration of 50 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. And we want to use the following data points. Part A would be 0 milliliters, part B 25 milliliters, part C 50 milliliters, and then part D 75 milliliters of sodium hydroxide that has been added. So that's what we need to do. We need to sketch the titration curve, right? We're titrating basically 0.1 molar HCl. So this is what we are titrating. And we're titrating that with 0.1 molar sodium hydroxide. So that is the titrant. And so we have these four different data points. And then once we have those data points, we can then actually sketch the titration curve. So for part A, we're starting at 0 milliliters of the sodium hydroxide has been added. And so this is our initial starting point, right? So no base has actually been added. And like a lot of acid-base questions, right, we always ask, what do we have initial in order to set up a type of pH calculation? And so in this particular case, right, all we have here is HCl, right, and that's 0.1 molar. That's really all we have initially because we haven't added any of the sodium hydroxide. So what is HCl? Well, this is a very strong acid, and that also means we have complete dissociation. So if we know our HCl concentration, which we do, remember that is equal to our hydronium ion concentration because of that complete dissociation. And from that, we can get pH. So part A here is really just a strong acid question. We know the concentration of HCl, thus we know the concentration of hydronium ion, and we can simply get to our pH. So our HCl, which is equal to that hydronium, right, is equal to 0.1 molar. And our pH, being the negative log of the hydronium, right, would be the negative log of negative log of 0.1, or we get a pH of 1.0 for the initial. So that's the beginning of a titration, and to be honest, that's always the beginning of a titration. Since you have not added any strong titrant, it's really just a classification of, okay, do I just have, something strong and complete dissociation like in this example, or maybe I have something weak and I have to worry about, maybe a Ka. But in this case, strong, so just complete dissociation. Part B is now when we've added 25 milliliters of the sodium hydroxide. So now basically the titration has begun. And as soon as the titration begins, this is a mole game, and we have to look at the neutralization reaction. What's left after neutralization then defines the pH. So as soon as that titration begins, we have now basically a mole situation, right? That we have to now define what's left over after that reaction is gone to completion. Again, remember, it's going to completion because we have very strong, very reactive starting materials. And then whatever is left is going to define the pH of the actual solution. So we have to start with that mole game, meaning that we had, for our measurement, 50 milliliters or 0.05 liters of HCl. Right, it had a concentration of 0.1 molar. So we end up with 5 times 10 to the negative third moles of HCl. And so that is, right, our initial mole value for the HCl. We do the same thing for where we're at in terms of the titrant. So in this case, right, we have 0.025 liters. We're also 0.1 molar in terms of the sodium hydroxide, and so we get 2.5 times 10 to the negative third moles of sodium hydroxide, right? And that's our added titrant. So those are the two mole values now that are going to be changing as we go through. The initial mole value of our HCl is basically a constant throughout the entire titration. But the titrant, namely the sodium hydroxide, is constantly changing. So we're always just looking at how the titrant affects basically what we're titrating, or in this case, how the sodium hydroxide affects the HCl. So here is where we now use our neutralization reaction to define now what is left over as a result. So we have our two starting materials, the HCl that we're titrating, the sodium hydroxide, that's the titrant, and that's going to produce water because of the neutralization reaction, and then salt as a byproduct. If we look at the initial set of conditions, we had 5.0 times 10 to the negative third moles of HCl. We have 2.5 times 10 to the negative third moles of our sodium hydroxide. And we would have 0 and 0 for our product, since initially we don't have either of those. So here, again, going way back into 31, right, our sodium hydroxide here is the limiting reagent, right? So that's basically going to go to 0 mole as a result. And that's telling us how the mole values are increasing or decreasing relative to that limiting reagent. And then once the reaction is done, we have the final set of conditions. And so we have these mole values now of 2.5 times 10 to the negative third mole for our HCl. We also have 2.5 times 10 to the negative third moles of our H2O, as well as the sodium chloride. Sodium chloride is really a spectator, so has, no pH effect. And in this case, we have left over strong acid, right? And this is going to determine pH. So once the neutralization reaction is done, we're trying to figure out what's left over as a result of that process to see, okay, what's left over, how does it affect the pH of what's left over? Some things aren't going to affect the pH, such as the sodium chloride. Other things can, and that's what we have to determine. In this case, we know water, has a pH of 7, but water is very weak in terms of its acid or base strength. Here we have a much stronger component that's left over, namely the hydrochloric acid. So that strong acid that's left over is going to determine the pH. So we have to now get back into terms of that concentration of the HCl. We have 2.5 times 10 to the negative third moles of the HCl, and that is in a volume now of 0.075 liters. The 0.075 liter comes from the 50 milliliters of the HCl that we began with, plus the 25 milliliters that we've now added from the sodium hydroxide titrant addition. And when we solve for that concentration, we get a value of 3.33 times 10 to the negative second molar in terms of our HCl. But remember, that's also our hydronium ion, because hydrochloric acid is a strong acid. So now we can define our pH of the solution by taking the negative logarithm of that concentration, and we get a pH of 1.47. So that's how we now have to really kind of keep doing that process that we just did in part B here again and again and again. These were just kind of extending the titration by more and more amounts of strong titrant, namely the sodium hydroxide. So in each part here, we have to do the same process. How many moles of the sodium hydroxide have we added? After the neutralization reaction, what is left over to affect the pH? And then calculate that pH. Part C now looks at 50 milliliters of sodium hydroxide is added. So again, it's just back to what we did in part B. You know, it's a mole game. It's a neutralization reaction. You know what is left over to affect pH. So it's exactly the same process that we did in part B. We already know moles of HCl. Right? Which was equal to 5.0 times 10 to the negative third moles. Right? That's what we're always beginning with, right? So we're not relying on part B. We're really, using part C as really a new question. And so we start with our initial set of conditions, which would be the HCl and this mole value of 5.0 times 10 to the negative third. And now what we need to then calculate is our new mole value for the sodium hydroxide. And we find in this case that those moles are actually equal to one another. So that means that if our moles of HCl is equal to our moles of sodium hydroxide, or another way to say that is our moles of H plus is equal to our moles of OH minus, this is the equivalence point. So remember, that's that special place in the titration curve where moles is equal to moles. We look at our neutralization reaction. Right, just like what we had earlier. So it's still the HCl plus the sodium hydroxide producing water and salt. And so we then do the same process. What's our initial set of conditions? Right, so in this particular case, we have the same moles of the HCl and the sodium hydroxide. No moles, so that means, in this case, both are limiting, meaning both go to 0. We have the same quantity of each one. And so that means we are producing that many moles in terms of our products. The salt, the sodium chloride, is never going to affect pH, right? So this is spectator, right? This is no pH effect. And the only thing left to affect pH would be the actual water. There's no hydrochloric acid left over. There's no sodium hydroxide left over. And so we just have this mole value of H2O. The pH of H2O, remember, is equal to 7. Right? All we have is that quantity of water, right? That means that, remember the auto ionization of H2O, pH was equal to the negative log of 1 times 10 to the negative 7th, or equal to 7.0. So even though we have, 5 times 10 to the negative 3rd moles of water, right, remember that water is going to, simply dissociate into equal quantities of hydronium and hydroxide, both in equal concentrations to get your pH of 7. For a, strong acid, strong base titration, the equivalence point is always 7. And the reason for that is since water is all that is left after neutralization. I mean, a pH of 7 isn't always the case at the equivalence point, and we'll go into an example later on showing that. But whenever we're talking about a strong titration or a strong acid, strong base titration, that pH is always 7 because of the fact that water is the only thing that's actually left over. For part D, now we've added 75 milliliters of that sodium hydroxide has now been added, right? So it's still the same, process, right? We still have that idea of the mole game. We still have that idea of the neutralization reaction. And then also, what's left, after neutralization to affect the pH, right? So it's exactly the same steps that we did in part B and part C. So we're still starting with that initial mole value of the HCl to be 5 times 10 to the negative 3rd moles. And again, that titrant is always changing, so we need to figure out its new mole value. So just doing a quick conversion from the volume and molarity to now our new mole value for the sodium hydroxide. And notice now that the tides have turned, right? In part B, we had excess of the HCl. In part C, the HCl and the sodium hydroxide were equal in mole value. And now we're past that equivalence point into part D, and now the sodium hydroxide is in actual excess. So we write our neutralization reaction just like we did in part B and part C to figure out what do we have left over to affect the pH. And so not even going to fill in the sodium chloride. Again, that's that idea of the spectator, right? There's no pH effect with it, so we really don't need to worry about it in terms of these types of calculations. For our initial set, we have the 5 times 10 to the negative third moles of the HCl. Now we have 7.5 times 10 to the negative third moles of our sodium hydroxide and 0 of our water. So now the limiting reagent is actually the HCl, right? And that is what's going to go to 0 moles after the neutralization is finalized or complete. So that is our change in mole value. Decreasing in terms of our starting material, increasing in terms of our product. And what that leaves us with after the neutralization reaction is basically excess strong base. Right? And this is what's going to determine pH. We do have water produced, but water is extremely weak in acting as a base. Sodium hydroxide, very strong. So our pH now, once we're past the equivalence point, is just determined by that concentration of excess hydroxide. So we can calculate that sodium hydroxide excess by now taking that mole value from above and dividing it now by 0.125 liters or 125 milliliters. This comes from the 50 milliliters we started with of the acid, plus now the 75 milliliters that we've added from the strong base titrant. And so that gives us a concentration of 2.0 times 10 to the negative second molar in sodium hydroxide, which is the same as our hydroxide concentration. We then can get our POH by taking negative log of that 2.0. And so our POH is equal to 1.69. And then our pH would be 14 minus the POH, or 14 minus 1.69 to give me a pH of 12.31. And that makes sense because we have excess hydroxide And we should expect a alkaline pH, a basic pH, a pH that is actually above 7. So now we can basically sketch the titration curve. If we go back to our conditions, right, at A, we had 0 milliliters of base added, and we had a pH of 1.0. In part B, we had added 25 milliliters, and we had for that a pH of 1.47. For part C, we were at 50 milliliters, and we had a pH of 7.0. And then we just did part D, where we were at 75 milliliters, and we had a pH of 3.1. So those are our, points that we actually need to now plot. So if we draw a titration curve, it's very qualitative here. Here are our volumes of titrants, right? Remember, this would have been 0. So that's part A, B, C, and D. So this is volume of 0.1 molar sodium hydroxide. Remember, the sodium hydroxide is that titrant. It's always changing its volume as we do the titration. And then in our y-axis, we have our pH. And so we're just looking at those data points to plot them on the graph. So at 0 milliliters, we had a data point at 1. At 25 milliliters, it really wasn't much different. It was a little higher, 1.47. At 50 milliliters, we had a pH of 7, or roughly there. And then part D, we had a pH of 12.31. So let's say something like that. So it kind of looks like you could just have like a continued upsloping curve, but it actually looks a little bit more like this. We would need a lot more data points to determine this. But what you find is a very flat region, and then we would have a very sharp increase or vertical line, and then it's going to basically flatten out once we are in excess base. So if we look at the beginning, this is where we have excess H plus, right? This is our strong acid region where we have excess of the HCl. And then in this region that we have at the very end, we now have excess hydroxide, or the strong base. So we have a really sharp curve. And then here is our equivalence point. And this should be now that idea of being around the pKa of indicator. We'll get more into that later. But that would be our equivalence point for the indicator that we would choose. And this is really kind of a telltale graph of a strong titration. If I were to look at, a strong acid, strong base titration, like we see above, we're always going to see that general type of curve as far as meaning that we're going to see that exact same curve that we see above, where we're going to have a very low pH, we're going to see a very large increase in the middle, and then we're going to have a very high constant pH. And again, we're going to have that pH of the equivalence point, being 7 for every single case in terms of strong. If we had a strong base, strong acid, as opposed, a different type of titration, but very much the same in terms of strong, we just have, kind of a flip of the curve. Meaning that now we're going to start very basic at the initial point, but again, it's going to be pretty flat. And then we have, again, that very steep curve, and then it gets flat again. But just like before, we're still going to have the pH at the equivalence point being 7.0. So whether it's strong base or strong acid, as far as the titrant, you're always going to get 7 when you're talking about a strong titration. So they're always going to have that pH of 7 at the equivalence point. We're always going to see very flat lines in front and in back of that equivalence point. And that's really indicative of a strong titration. The next example that we would get into in the next video will be now looking at a weak strong scenario. Remember, the titrant always has to be strong. Now what we're changing is what we're titrating. As far as, in this example, we were titrating a strong acid. What if we change that up and we were titrating a strong base? So look to the next lecture for that example. Now that our plot is done, we can then go into our choice of indicator. Remember, indicators are these chemical dyes. And if we look at our choice of indicators, we need, maybe a table to kind of help us out with that. So here we have, indicator, choice, and then we also have pKa for the indicator, and then a change in basically color, as well as pH range, and that would be of our equivalence point. So we have these 4 different columns as far as it goes. So for our methyl yellow is kind of our first indicator. There are a ton of indicators, that are out there. They all tend to have these color names with them, such as methyl yellow. The pKa of methyl yellow is 3.5. So the pH range that it could handle for the equivalence point would be 2.5 to 4.5. And that's actually going from yellow to red in terms of its color change. Another example would be bromothiamyl blue. Bromothiamyl blue has a pKa of 7.0, so it has a range of 6 to 8 in terms of pH, and that actually goes from a blue to a green color. We also have bromo crescent green. This actually has a pKa of like 4.6, so it can change colors from 3.6 to 5.6, and actually looks very similar to the bromothiamyl blue. And then one that you've had some work with in a lab, most likely, is phenolphthalein, which has a pKa of 8. So we're looking at a range from 7 to 9, and that goes from colorless to pink. So if we looked at that sketch that we did earlier, right, I'm doing it pretty general here, where we have our titrant, right? We were at that middle piece as far as the 50 milliliters is concerned of that titrant. And for our pH, at that equivalence point, remember that we were at a pH of 7. So we had this curve that was pretty flat, and then we had a really vertical sweep, and then it became flat again. So you want pKa of indicator to be around 7. So as a result of that, bromothiamyl blue is the best choice of indicator as a result. So again, once we know that once we know the pH of the equivalence point, right? In this case, that pH was 7. We just want to then pick an indicator whose pKa is around that 7 for this particular example. So in this case, bromothiamyl blue. You could probably get away with phenolphthalein as well, since it has that range of 7 to 9. But bromothiamyl blue, that's really right in the middle, pretty much spot on. So that would be your best choice of indicator.